Okay, so I'm recording my optimization makeup problem, and this is the one with the rain gutter. So how I looked at it from the problem that it gave me, I thought, so I need to find the maximum volume that can fit in this gutter. And so what I thought is that it's not a problem to do with volume, but it's with the intersection of the 3D figure itself, which is the isosceles trapezoid. So if I find the maximum area of the isosceles trapezoid, then I will know at what this angle, at what angle does the maximum, what is the maximum volume that can pass through the drain. So what I did was, because, so I named it like a trapezoid, if we're looking at it at like a trapezoid. So what I did was AB is like this CD, so that means that this angle and this angle are going to be the same, and this is 180 minus theta. Then what I did was I found the formula for the trapezoid, which is AB plus CD divided by 2 by H, and we're gonna name this H. So AB is the smaller segment here, and DC is the bigger one. And the bigger one, because it's an isosceles trapezoid, that means that this part here is 10, and this part here I'm gonna name it X because we're gonna have to substitute it. So my approach to the problem was essentially to find a way how to substitute both X and H, so that the only unknown that we have is the angle theta, which is what we're looking for. So how I did it was I looked at, because this is a right triangle, so here is a 90 degrees angle, I looked at it this way, so I could use a cosine and sine formula. So sinus theta, sine theta, sorry, is equal to H divided by 10, which means that H is equal to sinus theta times 10. And cosine theta is equal to X divided by 10. This is like the trigonometric rules. So X is equal to cosine theta times 10. And next, I have sort of two solutions for the area, finding the area. So I thought first I could do it like with the regular formula, which is this one here. And it turns out to be something like this. So I just sub in these for their values here. And what I discovered when I was solving this first version was that there is a lot more sort of, when you derive it, it gets a lot more messier. So what I did was use another formula. So essentially the surface area of this figure, the trapezoid isosceles, is these two triangles, their area plus the area of the rectangle. And these two triangles, the formula is just for the right triangle. So essentially S of this whole thing is equal to S of the rectangle plus 2 times S of the right triangles. And this is much easier because S of the rectangle is essentially 10 times H. And then plus 2 times, I'm going to use the formula with both, not the hypotenuse, but with both of the other side of the right triangle. So 1/2 times X times H. So this times this divided, and this cancels out and it becomes much easier then. So it essentially becomes XH. And the next thing that I do is sub in these values here in this. So I do like this. S is equal to 10 times sine theta times 10 plus XH. So sinus theta times 10 times cosine theta times 10. and then I multiply them, so it's 100 times sinus theta plus 100 sinus theta times cosine theta. I put these for the deriving. And the next thing I do is, so essentially I sub in the values. And then the next thing that I do is find the max area. So to find the max area, as for most of the optimization problems, I just do the first derivative. So the derivative of s has to be equal to 0. So this entire thing as 100 sinus theta times cosine theta, its derivative is equal to 0. So then I